Welcome to our journey into the world of databases. In today's digital age, data is everywhere, and databases are the backbone that help us store, organize, and retrieve this information efficiently. Whether you realize it or not, databases power many aspects of our daily lives, from social media platforms to online shopping and even your favorite streaming services. In this video, we'll break down the fundamental concepts of databases, making them easy to understand for beginners and those looking to refresh their knowledge. Let's start by exploring what a database actually is and why it's so important in our modern world. Database is essentially an organized collection of data. Think of it as a digital filing cabinet where information is stored in a structured way, making it easy to find and manage. Databases can store anything from customer information and product inventories to financial records and multimedia files. The main goal is to ensure data is accessible, consistent, and secure. As we move forward, you'll see how databases are designed to handle vast amounts of information, supporting everything from small businesses to global enterprises. Databases come in different shapes and sizes, each designed for specific needs. The most common types include relational databases, NoSQL databases, and object-oriented databases. Relational databases organize data into tables, making relationships between data points easy to manage. NoSQL databases, on the other hand, are more flexible and can handle unstructured data, which is perfect for big data applications. Object-oriented databases store data as objects, similar to how programming languages like Java or Python work. Understanding these types helps you choose the right database for your project. Relational databases are perhaps the most widely used type. They store data in tables with rows representing records and columns representing attributes. Each table can be linked to others through keys, allowing for complex relationships and queries. Popular relational database management systems (RDBMS) include MySQL, PostgreSQL, and Oracle. These systems use structured query language (SQL) to interact with the data, making it easy to insert, update, delete, and retrieve information efficiently. SQL databases are designed to handle large volumes of unstructured or semi-structured data. Unlike relational databases, they don't rely on tables and rows. Instead, they use flexible data models like key-value pairs, documents, graphs, or wide columns. This makes NoSQL databases ideal for big data, real-time web apps, and scenarios where data requirements change frequently. Examples include MongoDB, Cassandra, and Redis. NoSQL databases offer scalability and performance, especially for modern applications. Object-oriented databases store data as objects, similar to how object-oriented programming languages operate. Each object contains both data and the methods that operate on that data. This approach is particularly useful for applications that require complex data representations, such as computer-aided design or multimedia systems. Object-oriented databases provide a seamless integration between the database and the application's code, making development more intuitive for programmers. Database Management System, or DBMS, is the software that interacts with end users' applications and the database itself to capture and analyze data. The DBMS ensures that data is consistently organized and remains easily accessible. It also handles tasks like security, backup, and recovery. Examples of DBMS include MySQL, Microsoft SQL Server, and MongoDB. The choice of DBMS depends on the specific needs of your application, such as scalability, security, and data structure. DBMS consists of several key components that work together to manage data efficiently. These include the database engine, which handles data storage and retrieval, the query processor, which interprets and executes database queries, the storage manager, which manages how data is stored on disk, and the transaction manager, which ensures data integrity during multiple operations. Understanding these components helps you appreciate how a DBMS maintains data consistency and reliability. Data models define how data is structured and accessed within a database. The most common models are hierarchical, network, relational, and object-oriented. Each model offers a different way of organizing data, impacting how efficiently you can retrieve and manipulate information. For example, the relational model uses tables, while the hierarchical model arranges data in a tree-like structure. Choosing the right data model is crucial for the performance and scalability of your database. Hierarchical data model organizes data in a tree-like structure, with a single root and multiple levels of related records. Each parent record can have multiple child records, but each child has only one parent. This model is simple and efficient for certain applications like organizational charts or file systems. However, it can be inflexible when dealing with complex relationships, which is why other models are often preferred for modern databases. Network data model expands on the hierarchical model by allowing each child record to have multiple parents. This creates a more flexible structure, making it easier to represent complex relationships. The network model is particularly useful in applications like telecommunications and airline reservation systems, where data connections are intricate. However, its complexity can make it harder to design and maintain compared to other models. Relational data model organizes data into tables, making it easy to establish relationship between different data sets. Each table consists of rows and columns, and relationships are defined using keys. This model is highly flexible and supports powerful querying capabilities through SQL. It's the foundation for most modern database systems, offering a balance between simplicity and functionality. Object-oriented data model represents data as objects, similar to how programming languages like Java or C++ work. Each object contains both data and the methods that operate on that data. This model is ideal for applications that require complex data types such as multimedia or engineering systems. It allows for better alignment between the database and the application's code, streamlining development and maintenance. Database schema defines the structure of a database, including tables, fields, relationships, and constraints. Think of it as a blueprint that guides how data is organized and accessed. The schema ensures consistency and integrity, making it easier to manage and update the database as requirements change. Designing a good schema is crucial for database performance and scalability. Tables are the core building blocks of a relational database. Each table stores data about a specific topic, such as customers or products. Within each table, rows represent individual records and columns represent attributes. This tabular format makes it easy to organize, search, and update data. Properly designed tables help ensure data consistency and reduce redundancy. Fields, also known as columns, define the type of data stored in each part of a table. Common data types include integers, text, dates, and floating point numbers. Choosing the right data type for each field is important for data accuracy and efficient storage. For example, storing a date as text can lead to errors, while using a date data type ensures proper validation and sorting. Primary key is a unique identifier for each record in a table. It ensures that every row can be uniquely distinguished from others. Primary keys are essential for maintaining data integrity and enabling efficient data retrieval. Typically, a primary key is a single field like an ID number, but it can also be a combination of fields. Choosing a good primary key is a fundamental step in database design. Foreign keys are fields in a table that link to the primary key of another table. They establish relationships between tables, allowing you to connect related data. For example, an order table might have a foreign key that references the customer table. Foreign keys help enforce referential integrity, ensuring that relationships between tables remain consistent and accurate. Indexes are special data structures that improve the speed of data retrieval operations. Think of an index as a table of contents for your database, allowing you to quickly find specific records without scanning the entire table. While indexes boost performance, they also require additional storage and can slow down data modification operations. Properly designed indexes are key to optimizing database performance. Normalization is the process of organizing data to reduce redundancy and improve data integrity. It involves dividing large tables into smaller related tables and defining relationships between them. Normalization helps ensure that each piece of data is stored only once, making updates easier and reducing the risk of inconsistencies. There are several normal forms, each with specific rules for structuring data. Normalization is the process of combining tables to improve read performance, often at the cost of increased redundancy. This approach is sometimes used in data warehousing or reporting systems where fast data retrieval is more important than minimizing storage. Denormalization can simplify queries but requires careful management to avoid data inconsistencies. SQL, or structured query language, is the standard language for interacting with relational databases. With SQL, you can create, modify, and query database structures and data. Common SQL commands include select, insert, update, and delete. Mastering SQL is essential for anyone working with databases, as it allows you to efficiently manage and analyze data. Select statement is used to retrieve data from one or more tables in a database. You can specify which columns to return and apply conditions to filter the results. Select is the most commonly used SQL command and forms the basis for most data analysis tasks. Understanding how to use select effectively is key to unlocking the power of your database. Insert statement allows you to add new records to a table. You specify the table, the columns, and the values to insert. This command is essential for adding new data, such as registering a new user or recording a sale. Proper use of insert ensures that your database stays up to date with the latest information. The update statement is used to modify existing records in a table. You can change the values of one or more columns for records that meet specific conditions. Update is powerful but must be used carefully to avoid unintentional changes. Always ensure your conditions are precise to maintain data integrity. The delete statement removes records from a table based on specified conditions. Like update, it's important to use delete carefully to avoid accidentally removing more data than intended. Deleting data is a permanent action, so always double-check your conditions before executing this command. Transaction is a sequence of database operations that are treated as a single unit. Transactions ensure that either all operations succeed or none do, maintaining data integrity. This is especially important in scenarios like transferring money between accounts where partial updates could lead to inconsistencies. Transactions are managed using commands like begin, commit, and rollback. ACID stands for atomicity, consistency, isolation, and durability. These properties guarantee that database transactions are processed reliably. Atomicity ensures all operations in a transaction are completed. Consistency maintains valid data. Isolation prevents concurrent transactions from interfering, and durability ensures changes persist even after a failure. Together, ACID properties are the foundation of trustworthy database systems. Database security involves protecting data from unauthorized access, breaches, and other threats. Security measures include user authentication, access controls, encryption, and regular audits. Ensuring database security is critical for maintaining trust and compliance with regulations. A secure database protects sensitive information and helps prevent costly data breaches. Backup and recovery are essential processes for protecting data against loss or corruption. Regular backups create copies of your database, while recovery procedures restore data in case of failure. Automated backup solutions and disaster recovery plans are crucial for minimizing downtime and ensuring business continuity. Performance tuning involves optimizing your database to ensure fast and efficient operations. Techniques include indexing, query optimization, and hardware upgrades. Regular monitoring and analysis help identify bottlenecks and areas for improvement. A well-tuned database delivers better user experiences and supports growing data needs. Scalability refers to a database's ability to handle increasing amounts of data and users. Vertical scaling adds more resources to a single server, while horizontal scaling adds more servers. Cloud-based databases offer flexible scalability, allowing you to adjust resources as needed. Planning for scalability ensures your database can grow with your business. Data redundancy occurs when the same piece of data is stored in multiple places. While some redundancy can improve performance, too much can lead to inconsistencies and wasted storage. Normalization helps reduce redundancy, but denormalization may be used for performance in certain cases. Managing redundancy is a key part of database design. Data integrity refers to the accuracy and consistency of data within a database. Integrity constraints such as primary keys, foreign keys, and unique constraints help enforce rules that keep data valid. Maintaining data integrity is essential for reliable decision-making and system operations. A view is a virtual table created by a query. Views allow you to present data in different ways without duplicating it. They can simplify complex queries, enhance security by restricting access to certain data, and provide a consistent interface for users. Views are a powerful tool for managing how data is accessed and displayed. Stored procedures are pre-written SQL code that can be executed as needed. They help automate repetitive tasks, enforce business rules, and improve performance by reducing network traffic. Stored procedures are stored in the database and can be called by applications or users, making them a valuable tool for efficient database management. Triggers are special procedures that automatically execute in response to certain events, such as inserting, updating, or deleting records. They help enforce rules, maintain audit trails, and automate actions within the database. Triggers are powerful but should be used carefully to avoid unintended consequences and performance issues. Database users are individuals or applications that access the database. Roles define what actions users can perform, such as reading, writing, or administering data. Assigning appropriate roles helps control access and maintain security. Proper user and role management is essential for protecting sensitive information and ensuring smooth operations. Database connection is the link between an application and the database. Connections can be direct or managed through connection pools, which optimize resource usage and improve performance. Managing connections efficiently is important for scalability and reliability, especially in high-traffic environments. Cloud databases are hosted on remote servers and accessed over the internet. They offer flexibility, scalability, and reduced maintenance compared to traditional on-premises databases. Popular cloud database providers include Amazon Web Services, Microsoft Azure, and Google Cloud. Cloud databases are ideal for businesses looking to scale quickly and minimize infrastructure costs. Data refers to extremely large and complex data sets that traditional databases struggle to handle. Specialized databases and technologies like Hadoop and NoSQL systems are designed to process and analyze big data efficiently. These solutions enable organizations to extract valuable insights from massive amounts of information, driving innovation and growth. Data warehouse is a specialized database optimized for analysis and reporting. It consolidates data from multiple sources, making it easier to perform complex queries and generate business intelligence. Data warehouses are essential for organizations that need to analyze large volumes of historical data to make informed decisions. Replication involves copying data from one database to another to improve availability and reliability. It can be used for backup, load balancing, or disaster recovery. Replication ensures that data remains accessible even if one server fails, supporting high availability systems and global operations. Database migration is the process of moving data from one database to another, often during upgrades or platform changes. Migration requires careful planning to ensure data integrity and minimize downtime. Tools and best practices help streamline the process, making transitions smoother and less risky. We've covered the essential fundamentals of databases, from basic concepts and data models to security, performance, and advanced topics like cloud databases and big data. Understanding these principles lays the groundwork for deeper exploration into database design, management, and optimization. Whether you're a student, developer, or business professional, mastering database fundamentals will empower you to work more effectively with data in any field. Stay curious and keep learning as you dive deeper into the world of databases.